Welcome to ROPYourself, self-ropping for fun and profit. My name's John McEllroy from MTSI, and I want to thank OISF for allowing me to give this talk today. A little bit of disclaimer, lots of things to look at, but let's get to the bottom line. If you don't have permission, don't do it, so be smart about these things I'm going to show you today. So what are we going to talk about? We'll do a little bit about me. I'll talk about some red versus blue perspective. We'll talk about history and the trends of malware evasion. We'll look at shellcode versus ROP, what this whole talk is about, and we'll talk about what is ROP. And then we'll look at some pros and cons. How do you ROP yourself? I'll show a demo. And then we'll talk about what's the big deal? Is it really worth doing all of this? What's the future of this stuff? And then how can you learn some more? And then I'll talk about how you can get any questions to me if you have. And I apologize for not being able to be here in person. I'm on the road traveling. But again, I thank the conference organizers for allowing me to give this talk anyway. Okay, about me. So I am a retired naval aviator. I was a test pilot, flew off of carriers. I'm also an expert in weapon systems and cyber as it relates to weapon systems. I lead a team of pen testers that focus on cyber physical and weapon systems at MTSI. We do a lot of software reverse engineering, a lot of exploit development. My hobbies are software-defined radio, CTFs, capture the flag events, and love smoking meat. And hopefully I'll see some of you guys in Vegas at Hacker Summer Camp. So let's talk about red versus blue. So there's two sides of this coin that I want to look at. When I talk about looking at a tool or a technique like self-ROP, we can always look at it from two perspectives. One perspective, the red side, would be, the red folks are using the same methods that the actual bad guys are using. I mean, they're constrained based on morals and ethics, but they're still trying to use the same techniques. So from that regard, the ability to evade detection is really important. Most of the time, people on the red side are trying to be quiet as much as possible and not make a lot of noise. However, on the blue side, those that are trying to defend, it's important to understand about some of these techniques also. It's important for you to know what to look for. You have a lot of data that you have to deal with, especially depending on the size of your enterprise. And sifting through that noise often requires the help of tools that can work with big data. But sometimes it's really important for you to also have your own bespoke tools, ones that are born out of Red Team. And those can provide a lot of great insight, because if your tools and your people can think like an adversary, you've got a better chance of sometimes finding them, especially the quiet ones. So I want you to keep this slide in mind as we go through the rest of the talk. And just keep in mind, depending on where you sit, whether you are on the red side or the blue side, there's value in understanding these techniques. Next, let's talk about malware evasion. Signatures are dead, long-lived signatures. The acronyms change over time. We can talk about antivirus, EDR, XDR, the next thing after that. They all promise bigger and better things and lots of fancy buzzwords and terms, but in my experience, they still have a large reliance on signatures. What do I mean by signatures? I mean, the simplest way to think about that would be hashes. You take a hash of a binary or a file and you get a unique fingerprint, but you took it of the entire file. That would be called a macro signature. If you look at a micro signature, you're taking a sliding window across the binary and you're looking at chains of contiguous bytes and looking for patterns in there. But it's still signature based. There's dangers in that, and we'll talk about where that can lead you astray later, or might benefit you if you're on the red side. Change is slowly coming with these tools. There's a lot of focus and emphasis on heuristics, behavior, telemetry, machine learning is big, detonation chambers, symbolic execution. All of these things are kind of the forefront in the ever-growing future of trying to detect malware. The problem is that these things sometimes come with a benefit cost, and there's always a trade-off with the vendors of these tools. They don't want the user to click on an icon and then sit there with this spinning wheel of death, right? You'd like the program to just come up and run. People want their computers to feel snappy. And so there's always a trade-off between how much do I analyze versus do I say that I think that's good enough and this program's probably safe and let it run. It will always be a cold war of sorts, a game of cat and mouse between the people that are trying to detect malware and the people that are writing malware. So that's certainly what I want to keep in mind. This slide, though, is meant to highlight the fact that we're really going to look at signatures. We're really going to look at how these tools look and what does self-ROP bring to that conversation. So let's now look at shellcode versus ROP and talk about what is ROP, the whole point of this talk. For those who aren't familiar, we'll do a small shellcode for beginners. What is shellcode? In summary and in a short definition, it's exploiting a vulnerability in source code where the user input can overflow a program buffer in memory. Overflowing the buffer in just the right way allows the attacker to control the program, take over its execution in a very precise way. The attacker inserts specially crafted bytes, so it's not just any bytes they throw into this buffer. They have to put in very specially crafted bytes that when they're executed by the program, they achieve whatever goals the attacker has. In our case, we're looking at a reverse shell. Many other types of attacker goals, but again, maybe you want to crash the program, but maybe you don't. Maybe you want to do something very specific. So shellcode is a very, very precise ordering of specific bytes to achieve this goal. How do we do that? So this diagram here shows a buffer in a typical program. And normally, when a program is operating the way it should, you have a buffer, and then you have some padding below that buffer, it's just some space on the stack that there might be other variables, there's other things. And then finally at the bottom of the stack, you have, for this particular function, you have the return address for the instruction pointer, where it's going to jump back to after it's done. And the goal of all of this, whether we're talking classical buffer overflows with shellcode or we're talking ROP, the goal of all this stuff is initially to take control of that register, that return address, to get the program to go to a place that you need it to as the attacker to achieve your goals. So how does this work for shellcode? You overflow into that buffer, into the padding, and overflow that return address with a new return address. And that return address, it actually will be an address on the stack. So you see the blue arrow there, you would put an address up into your shellcode so that when you return, you jump up into your shellcode and start running it. Sometimes it can be referred to as a trampoline because you're bouncing back. This has worked great for many, many years. It does have some limitations though. You have to know the specific location of your shellcode in memory. And when I say specific, I don't mean down to precise byte, but I mean generally you have to know a very narrow area of memory where your shellcode resides. If you don't know this, you're not going to be able to get your shellcode to run. You're not going to be able to jump into it. There have been a lot of new protections implemented in operating systems and in CPU architectures to try and mitigate this problem. One of them is ASLR, Address Space Layout Randomization. What it does is when it loads up a binary into memory and loads up various libraries and other things, it randomizes the locations for all that. It randomizes the location for the stack. And so if the buffer was at a certain stack location when the attacker was testing it on their computer, and then they go to throw this exploit at the live computer on the target, the addresses are going to be completely different. And so, it wouldn't work. One of the other big protections is what's referred to as DEP, Data Execution Prevention, or NX, the no execute bit. What that means is the operating system keeps track of where the executable code for a program is versus where the stack is that should have sort of scratch values and temporary values for functions and arguments and things like that. And if it detects that the program is trying to execute actual opcodes off of the stack, it'll say, I'm sorry, you're not supposed to do that, and it'll crash the program, terminate the program, in fact. Both of these, ASLR and DEP, are very effective at stopping traditional shellcode from running. Shellcode no longer works because of ASLR and DEP. What's next? In comes ROP, return-oriented programming. There are different variations of return-oriented program. RET to libc, return to libc, is a specific kind of ROP where you're jumping to whole functions inside of libraries. There's also jump-oriented programming. It's a related cousin to ROP. All of these things rely on one fundamental concept. You use a program's inherent code against itself. What do I mean by that? You trick a program to execute its own code, but in a different order to achieve attackers' goals. And I have some examples to show you what this looks like. You basically use small snippets of code referred to as gadgets. What is a gadget? Take, for example, on the left side of the slide, I have the main function in a typical program. And you can see in main, I call a series of subfunctions, A through D. If I look at the code, the source code for my functions, like for example, I look at function B and function D, you can see I would have some lines of code in these functions, and then when I'm done, I have a return so that that function can then go back to main, and main can execute the next function. Those of you that may have written programs, a very, very familiar thing to see. But let's make that jump and transition from C code or some other coding language to assembly and look at a lower level. If I look at function B, I'll see that I have lines of assembly that are doing various things, and maybe I've got this line at the end that does an XOR of RAX with RAX. For those who aren't familiar with assembly, when you XOR a register with itself, the result is 0. So you basically clear out the register. This is a shorthand or shortcut in assembly to zero out a register. So I've got in function B at the end, I've got this opcode, this XOR opcode to clear out the RAX register, and then it returns, hence the RET opcode there in x86 assembly. If I look at function D, I've got some assembly lines, and then I've got a pop RCX. What that line is going to do is take a value off the stack and put it into the RCX register, and then it returns. These just happen to be there because of how the compiler turned your higher level language into assembly for these functions. They weren't necessarily planned to be there. That's just the opcodes that the compiler picked to achieve the functional goals of the functions B and D. We'll find how these can be useful when we take them in pieces and rearrange them, though. If I take the ends of function B and D, the XOR, RET, and the pop and RET, I now have two gadgets, gadget 1 and gadget 2. They each do very specific, limited things. They might do one thing with run register. They might do one mathematical operation, and then they return. And that's okay. I want them to be small because I'm going to gather a whole bunch of them and reorder them in a way to achieve a larger program. So let's look at a small little notional shellcode. Let's say, for example, in this shellcode that at the end of it, I want RAX to have the value 0 and I want RCX to have the value 2. I can do that very simply by doing an XOR of RAX with itself and then popping 2 into RCX. So you can see on the left hand of the screen in blue, I've got my desired shellcode. I'm going to show you how I can take the gadgets from the program itself and reorient them and reorder them to achieve this shellcode. So again, I'll focus on function B and function D, looking at the assembly, and I put in some notional addresses now for each of the opcodes in function B and function D. So now my gadgets not only have opcodes with them, but they also have addresses for where they reside inside the program. So for example, the first gadget, the XOR RAX, that is notionally found in the program at hexadecimal address 3096. And the second gadget, the pop RCX, is found at address 3044. So looking on the right side of the slide, back at my buffer overflow diagram that we saw before with shellcode, instead of overflowing the buffer all the way down to the return address to jump back into the stack into my shellcode, now what I do is I simply overwrite the return address on the stack with the address of my first gadget, and then subsequently addresses of my next gadget and my next gadget and so forth. So you can see I put onto the stack address 3096, and then address 3044, followed by the value 2. I'll talk about why that's there in a second. So what happens now is when this buffer is overflowed in a given function, when the function goes to return, it goes to this location on the stack, thinking that it's going to get the address to jump back to where it came from, main or some other function. But instead what it finds is the address 3096, and it dutifully jumps there. And it goes into address 3096, which goes into the middle of function D. It runs XOR RAX. It doesn't care that it's in the middle of a function. It doesn't care that it wasn't the original function that it was supposed to go to. It just says, I'm going to go there and I'm going to see valid opcodes and I'm going to execute them. So we go to 3096. We XOR RAX with itself. That zeroes it out. And then the ret call is made at the end of function D. And what that ret call does is it goes back to the stack and finds the next value. And what does it find there? The value 3044, which it jumps to. And that jumps into the middle of function B. And now it's popping RCX. So when it pops RCX, it goes and looks on the stack. And what does it find? It finds the value 2. And it puts that into RCX. And then it calls ret. And if I had more things to do in my shellcode, if I was more complex, I would have more values further down past the 2. Another address for another gadget, another address, and so forth. In this case, I had a very simple shellcode that was comprised of only 2 opcodes. And this is the basis of ROP. This is how you take individual pieces of functions that are already there inherent in the code, and you execute them in a different order to achieve whatever goal you need to. That sounds great. That sounds wonderful. How does it work in practice? Let's look at some pros and cons for ROP. Is it really better than shellcode? Well, one of the cool things about ROP is you no longer need to insert shellcode. I no longer need to take actual opcodes and try to shove them into an input buffer and shove them into a program to get them to run. That can be very advantageous, especially when I've got scanners that are looking at network traffic coming in, looking at file uploads and things like that, looking at user input. I no longer need to get shellcode past any input validation functions. A lot of times input will get validated when they're looking for things like maybe carriage returns or null bytes or other things, and I don't have to worry about that for the shellcode. Now, we still have to worry about input validation. I'll talk about that soon, but I don't have to worry about my shellcode getting looked at. A lot of times, that's where the signatures come into play. They'll look at those strings of bytes and say, this looks like shellcode, I'm going to stop this, right? Whereas ROP is just a collection of addresses. And if you don't know the specific program, the addresses won't really make much sense. They're certainly not going to look like opcodes. The cool thing about ROP is the program itself becomes the shellcode. This is how we bypass DEP. The program itself has executable code. That's what it's made for. It's a program. It's meant to run. We're just going to run it in a different order than the author intended it to. We also no longer need to know specific locations in memory. This is how ASLR is bypassed. The text address is generally the same. Now, there's some limitations and caveats to that. There are some new compiler features out there where you can randomize everything, and that can certainly mitigate ROP. But for most of the cases, the part of the binary that actually has the opcodes in it is always going to be loaded at the same address location in memory. And so you know where those gadgets are and you can run them. What are the downsides to ROP? Well, it is completely dependent on the functions that are found in the victim binary. With shellcode, I can do anything that I want as long as I can get the bytes in there. But with ROP, I can only jump to gadgets that exist in the program or the libraries that it is using. And I need to know the addresses for those. So if there's not a gadget in the program that I need, then I'm kind of stuck with that. I'm kind of run out of ideas to be able to do what I'm trying to do, and I sometimes have to get creative in other ways. Oftentimes, to do ROP, you have to do some custom arrangement of ROP gadgets. They do not always fit together easily, like when you're building shellcode. Because you're trying to misuse a program in a way it was not designed to. And so you might have a gadget that has what we like to call collateral damage. It might do what you want, but it also might do some other things, just because that's how the program was written. That's how the compiler and the assembler did their thing. And you have to kind of live with that. And so you have to do some creative workarounds to get your ROP chain to achieve your goals while not crashing the program or so forth. So it can take a lot of manual custom work. It's still more of an art than a science trying to build ROP chains. And it has to be for each specific binary. If someone compiles the binary again, all your ROP gadgets may have changed. Some might be not there anymore. The addresses have changed, and so you got to start that all over again. Another thing to note is in order to do ROP, as compared to shellcode, you still have to overflow a buffer. Still need to be able to control the return address, and so you still have to have some way of going past the bounds of some memory buffer on the stack and getting down to the return address. So if you've got lots of good mitigations and code reviews and other things to prevent buffer overflows, this is a great way to stop ROP also. And like I said before, even with ROP, you still have to deal with input validation. Oftentimes things like null bytes, bytes of 0, those can be an inhibitor to getting ROP chains fully through, just as they are with shellcode. Now, finally, what the whole talk is about. Up till this point, we've talked about perspectives. We've talked about a little bit about malware evasion. We've talked a lot about shellcode and what is ROP and how it's different from shellcode. Let's talk about what happens if you ROP yourself. What do we mean by that? Well, what if the attacker was the victim? What if you had a vulnerability in your own program as the attacker? What as the attacker you overflowed your own buffer? And you fill your program with many useful gadgets, you hijack your own program, you run a hidden ROP chain inside your program. That's what we're talking about when we talk about ROPing yourself. We'll talk about why you would do that in a bit, but that's it in a nugget, is you're basically going to attack your own program to run a hidden ROP chain. How hard would that be to do? What's really involved in trying to make that happen? And what would it get you? What do you gain out of that? Let's make it real. Let's get down to brass tacks and get pragmatic. In order to ROP yourself, you do need a hole big enough inside your program to hold your ROP chain. And when I say a hole, I mean space in the data section of a program to have all those addresses of all those ROP gadgets laid out. So you need space for that. You do also have to deal with a bit of the chicken and the egg problem, meaning you write a program, you compile it, you look for ROP gadgets, and then you're like, oh, I'm going to take that and I'm going to take those addresses and put them back in to build my ROP chain. But in doing so, when you edit the source code and then recompile it, you shifted things around, the compiler changed things up, and now your gadget addresses are different. And now you got to go through that whole cycle again. So that becomes a real hard thing to get around. It becomes difficult if you're trying to do all that manually. I do want to talk about what we gain out of this. So when you talk about ROPing yourself, we really confuse static analysis and any kind of initial reverse engineering review. If someone or some sophisticated tool were to try and do some actual execution of a program that ROPs itself, it would eventually find out what the program really wants to do. So ROPing yourself really only addresses the initial static analysis. Now that's not a waste of time. We talked about before the trade-off with EDRs and antivirus and about how they are always trying to make sure that they don't analyze too much to annoy the user. And there's always a timing trade-off. And so they often will start off with static analysis. And if you can get past static analysis and look benign enough, the system will let you run. And that's the goal for this, is to get back past that initial static analysis. There's still a need, if you really want to operationalize this, to use enhanced obfuscation techniques, anti-RE, anti-VM, anti-debug, all of those things, to make sure that if a tool or a person takes the program and says, okay, I'm going to put you in a virtual machine and let you run and see what you do, that it would still stay benign unless it knew it was on the full target system. So I want to be clear here. This is not sort of a single shot of ROPYourself and it does everything and you can get past everything. It just addresses that initial static aspect, and it has some very, very powerful effects in that regard, but it shouldn't be used by itself. We'll talk more about that here in a second. But the good news is when you're ROPing yourself versus trying to ROP somebody else's program, you control the binary. Remember, we talked about before, one of the limitations of ROP is you have to live with the programs as they're compiled with the gadgets that are in there. But if you control the program, you control the source code, you can put whatever you want in there. So if you need a gadget, just put it in the code. That's very, very powerful for you to be able to do that yourself. There are numerous tools to find gadgets. We'll talk about them in the demo and here at the end of the brief. And there are some automated tools, but there's not a lot. This is still a very manual process trying to do this whole thing. And I'll show you how I tried to do some automation using scripting and Python during the demo. So again, what do we gain out of this? Many defensive solutions rely heavily on static analysis of binaries for performance reasons. So self-ROPing, that really brings in strong baked-in obfuscation for that. It's very powerful, and I'll show you some measurements that I took that kind of highlight that aspect. For example, here we see that this was the standard Metasploit TCP reverse shell for Linux binary. So Metasploit, that very powerful hacking tool, you can have it build binaries for you. And I said, hey, build me a binary for Linux that will do a very simple TCP reverse shell, meaning on the victim machine, the malware will reach back out to me to make a connection. I had Metasploit make that binary and I threw it up to VirusTotal, and you can see it got caught right away. Now, I don't want you to walk away going, yeah, but look, it was only 6 out of 62. The reason that number's so low is many of the AV solutions are focused heavily on Windows and not on Linux. I do want you to focus on the fact that there were detections and that they came up and said, hey, this is, a bad thing. Example here is Microsoft Defender doing a scan of this same Metasploit binary, and you can see that it comes up and says that it's Linux, and it talks about the binaries there to try and get a shell, and it's a backdoor, and it catches it right away. Okay, so that was straight up out of Metasploit, and these tools, they do signature analysis, initial static analysis, and they grab this and they trash it right away and say this is bad. Here is an example of building a binary where we ROP ourselves and we do our own ROP chain. We overflow our own buffer and run our own ROP gadgets to achieve the same functional goals as that Metasploit code. We do a reverse TCP shell. And you can see nobody catches it. Because when they do the initial static analysis, it looks like a benign program. It looks like a program that just does some stuff and copies some buffers here and there and maybe does some printfs and so forth. I'll show you more of this in depth during the demo. Here you can see that same ROP binary getting scanned with Microsoft Defender, and Microsoft Defender says 0 threats found, no current threats. All right, now let's get into a demo, and I'll show you exactly how this works down at the source code level, and we'll see real-time running the ROP gadget chain on ourselves and getting a reverse TCP shell. Okay, let's take a look at a demo for this. So here we can see in this screen I've got the standard Metasploit TCP reverse shell, the assembly listing for that, the opcodes, and then the raw bytes. You see the raw bytes on the left and the opcodes on the right. This was taken straight from the source code of Metasploit. These are the bytes that are being signatured by lots of AVs and EDRs out there. So we're going to try and replicate these bytes using our self-ROP technique. And you can see all of these calls here. They're setting up registers and making system calls, and then setting up other registers and making system calls. I've broken down the opcodes over here to kind of understand them a little bit more, and you can see that that gibberish that we looked at just a second ago starts to become a little bit more clear in that we're making a socket system call to set up a TCP socket. And then after that, we connect to the socket and get a file descriptor for that. That's where we set up a IP address and a port. Here it's defaulted to the standard Metasploit localhost and port 5555. We could make it anything that we want, but for the purposes today, we just kept it this way. So we make a connect to that socket, and then after that, we go through a loop where we connect up our standard in, standard out, and standard error of our process to that socket. That's how we get our input and output out across the socket to us on the other end. And then finally, the last thing that we make is an exec VE call to bin sh, and this is where we actually run the command, the shell that we want, and connect it up to the socket. And then on the other end, we'll be able to issue commands on the target or the victim machine. So now that we've broken down all the assembly into the various register values and system calls, now we can figure out how do we replicate that via ROP inside our own program. So the first thing we have to start with is our ROP shell, or our ROP harness, if you will. This is going to be our own quote-unquote victim program that we're going to try and overflow our own buffer and then run our own ROP gadget chain. So I've got some standard C here. It's very simple. You can see in the main function, I've got some, just basic print statements and some functions that get called. They look kind of normal, right? If you were to just look at the source code without really digging deep, you would look at this and say it looks like it's doing some sort of installation and calculations and things, and that's about it. If we take a look at this start install function, what we see here is that it at its core does a mem copy. It copies one section of memory to another. And the key is the fact that it's copying into this data buffer, which is only 16 bytes in size. But it's taking this source buffer and it's copying way more than 16 bytes. Now, there's not a specific number here because, again, I was trying to obfuscate the source code and make it look somewhat benign. But when you run these numbers and have the program actually execute itself, you'll find out that this turns out to be 59 bytes getting shoved into a 16-byte buffer, and this is where the overflow happens, right here. And so the ROP chain kicks off right at the end of this start install function. Now I have some other functions in here that look like maybe they were left over from development or dead code or what have you. But what you can see here is that I've got actual assembly code that I've embedded inside my C code. And this is what I was talking about before in the slides, which is if you don't have a gadget and you're trying to self-ROP, you can just put it in yourself. And that's the beauty about this. So I needed these two particular gadgets. I could not find them in the original program that I was compiling, so I just stuck them in. These functions don't run. If you tried to run them, they would crash the program. They just sit in there and they basically sacrifice themselves to allow me to have the gadgets that I need. This is another kind of obfuscation function that just obscures the true numbers of the fact that we're taking a very large buffer and trying to shove it into a small buffer. This is where the actual ROP gadget chain lives. This is just a data array inside the C program. The first several values in this array are just padding. They're dummy values that are meant to get us overflowing the buffer down to controlling that instruction pointer register. But from this point on, all of these are either valid addresses to gadgets in my program, or they're arguments that I'm trying to use, like putting a value into register or loading a value into memory. So you'll notice right here, like this 29, you might remember that from when we looked at over here, the source code for that Metasploit TCP reverse shell, right? So all of this is the ROP chain, and these just get fired off one by one. So it goes to this address, does the gadget, does something with this value, puts it into a register, then it comes back and goes to the next gadget address, and so forth, all the way down to the end. And by the time it gets down to the end here, it will have created a socket, connected to it, connected up my inputs and outputs, and then run bin.sh. So when I wrote this program, these were just empty values, right? I didn't exactly know what was going to go in there. I had a rough idea, but I needed a hole big enough for my ROP chain. Later on, I filled them with these specific values that you see here. So I just take this C code and I compile it, and then I run some tools to look for ROP gadgets, and then I make note of which ones that I want, make note of the addresses, and then put that together to edit this C code back up again with the exact values that I want. So you can start to see how this would be very manual. You could start to see that you could make one change and then it changes everything and you have to go back and do it all over again. So I said, maybe I can try to script this up or automate this a little bit more, at least make it a little easier for myself. So the first thing that I did was I made this bash script, and so it does the compilation for me. Notice here when I'm compiling that I tell the compiler I don't want any stack protection, no stack canaries or anything, because I need to smash my own stack. So that's very, very important. So I do the compilation here and produce the binary. And then I run this tool called ROPYgadget. I'll give you the link for this at the end of the talk. It's a really useful tool. I use it a lot. This and another tool I'll talk about. But ROPYgadget will basically search the binary and look for the gadgets that I need. And here I'm just taking the output of that tool and I'm putting it into a file. I run it twice simply because I needed a specific type of gadget called a multi-branch gadget. One that was required for me to be able to do the syscalls and then still come back to my ROPYgadget chain. So that's why I run that tool twice. I basically take these gadget listings now and I grep through them to find very specific gadgets that I'm looking for. You'll find that there's lots of gadgets out there. Some of them have what we like to call collateral damage, meaning they'll do what you want, but they'll also do other things like maybe mess up other registers or write something to memory. And you either have to live with that collateral damage or you got to find some way to undo it. If you can find a very, very clean ROPYgadget that does exactly what you want and then returns back to you, that's the golden thing. That's the best thing in the world. So here I'm grepping for those very specific gadgets to do what I'm interested in. So for example, this one will simply take a value off the stack and put it into the RAX register, and then we'll return back to my ROPYgadget chain. This one here does the same thing for RDI, so you can see I do that to be able to load up the key registers that I need. This was the one that I needed the multi-branch for. It was a specific ROPYgadget that calls syscall, which normally you would go away somewhere else for, but I needed to call syscall and then come back and then do a return so I can get back to my ROPYgadget chain. And then, there's some more complex ones. Here's one that I needed specifically because I needed to be able to load a value into memory and then have a pointer to that in the RSI register. So that one started to get a little more complex. So I take all of these and I put them into this file called list.txt. I'm basically building up my library of specific gadgets that I need. I add some metadata to it using sed, basically the command line editor. The reason I do that is later I'm going to pull these values from this list.txt into a Python script, into a dictionary, so that I can automatically grab them and use them as I need. So I add this metadata. These are like labels. This is my way of thinking about what these gadgets are. This last one, it's not a gadget, but I needed to know the location of the /bin/sh string inside my binary. There is a way to load this string in manually and to put the bytes of that string into the ROPYgadget chain, just like any other value that you want to load in. But a lot of times, if a program already has the string in it, you can just reference its location. And given that I'm self-ROPing, I can easily put that string in. In fact, I think over here, I've got, here is a printf where I specifically put in some nonsense statement about installation and requirements, but I made sure that I had /bin/sh in the program already. So once it's in there, all I got to do is search for it and I can get the address for it. So that's what this does with ROP gadget. I'm not looking for a gadget specifically, but now I'm looking for a string, so the dash dash string, and I'm looking for /bin/sh, and I basically put that into my list. So what does that look like when I run this whole bash script itself? I get this. So you can see here that I've got a line for each gadget. On each line, I've got the label that I'm going to use when I parse this in Python into a dictionary. Then I've got the address inside the program for where that gadget resides. And then I've got the actual gadget itself. And so you can see each of these gives me all the things I need. I can load up registers, I can make a syscall, I can move the RAX value into RDI, and I can also load up a value into memory and then the pointer for that memory area into RSI. I have the value for the bin/sh string also. Now these are by no means the only gadgets you might look for. It really depends on your program. In my particular case, these were the minimum gadgets that I needed to achieve a TCP reverse shell with those several syscalls we talked about: the socket, the connect, the dupes, and the exec VE. So now that I have this list of gadgets, specific gadgets, this is where I built a Python program to take all those gadgets and try to build up my ROP chain with my specific addresses so that I can copy it back into my program and recompile it. Yes, I know maybe some of you in the audience are thinking, hey, why didn't you just combine the bash script and the Python build script and just make it all one big thing? And I could have done that. I just for this first go around, as I was working on this and doing this research, I built two separate things. It could definitely be optimized and put probably into one big mega script to do it with one single button push. You can see here that padding I talked about at the top of that data array inside the source code. Here I've got that in my Python script because I'm going to build that array so that I can put it back into my source code. I've got a function that basically takes my gadget ROP chain as I build it and print it out in a pretty way that allows me to copy and paste directly into C source code as a data array. The other functions, the majority of these other functions are basically me implementing building the ROP chain as I go. So I've got a function for each type of gadget that I want, and what it does is it goes out into that dictionary. It finds the address of the gadget based on that list.txt. It finds it in the dictionary and it puts it into this chain that I'm building along with any values that it needs. So for example, when I'm popping RDX, that means I'm going to take a value off the stack and put it into the RDX register. Well, I need that value. So in addition to getting the address of the gadget, I also get the value and I put those two onto the gadget chain. The nice thing about doing ROP with Python this way is that when you build up these functions to kind of build your gadgets for you inside of Python, at the very end, what you get to do is you essentially get to almost write pseudo assembly, where you're making these function calls inside of Python with arguments, but when you look at it and you label things the right way, you can see here that this Python code starts to look very, very similar to the original reverse shell assembly that we saw out of Metasploit. I'm popping values into registers, I'm making a syscall, I'm moving RDI into RAX, I'm loading a pointer into RSI, and so forth. So that's what's really powerful about doing it this way is I don't have to try and piece things together so manually. It becomes a little bit more abstract, a little bit easier to deal with. So I build all this, and when it's done, it prints out basically a huge long listing of this. And I get to paste this directly into my source code and then compile the program again. So this process really sped up quickly my ability to look at different addresses of gadgets, to change the program, and now all the addresses change. I don't have to write things down or keep track of everything. I just run these programs and it just catalogs it all, builds a new ROP chain, and I just paste it in and I'm done. So let's take a look at what that would look like now. So if I come over here, the first thing I'm going to do is I'm going to run GDB and take a look at the program as we try to step through. I want to show you what this ROP looks like as it's actually executing. So the first thing I'm going to do is disassemble the start install function, because if you remember, that is where the overflow happens. That's where the mem copy happens of a big buffer into a small one. So I'm going to set a breakpoint at the very end of this function, at that ret, because that's where it jumps off because of the overflow, jumps off into my ROP gadget chain. So I'm going to set this breakpoint. All right, my breakpoint is set now, and I'm going to hit run, and the program should run all the way from the very beginning all the way through down to this function right at the bottom of this function. And now you can see, by the way, if I come over to my source code here and I look at start install, who calls start install? Main. Main calls start install, right? So when start install is done and the program is acting, shall we say, normally, it should go straight back to main. But that's not what we're finding here. What we're finding is at the end of start install, it's jumping to, no surprises there, it's jumping to a gadget in some other function inside my program, just a tiny little gadget, popping RAX, and then returning. So if I single step through this, right now, just so you see there's no surprises, RAX has the value of 0A. It's going to jump to pop RAX, and you can see, by the way, what's on the stack here is right below the address of the first gadget is the value 29. So if I do a single step here, now look at where the stack pointer is pointing, is at on the stack where the value of 29, hex 29 is on there, and the next opcode to run is a pop RAX. So when I execute this, RAX will now have a value of 29. So if I single step again, and we look up here, we can see RAX does indeed have a value of hex 29. So we have run our first gadget. Well, almost. We still have to return. We still have to run the ret. So it's very important. Gadgets are not just the operation you're trying to achieve, but you also have to have some sort of return or jumping to get back to the next address of the next gadget. So if I single step again, you can see I have now moved on to the next gadget, where I'm going to pop RDI, and then I'm going to pop RSI. So I'm just going to single step through these here and show you all the way down to the syscall. So this is really cool, what GDB does. It's really smart about these things. It says, it sees the syscall, and it looks at the register values and says, oh, I know what that is. That's a socket. And it even shows me the arguments for the socket call. And so this right here shows you that we ran our program and overflowed our own buffer, jumped into our ROP gadget chain, began to execute a series of gadgets, all the way down to doing syscalls. Now, I could step through this whole thing, but believe me, it works, because I wanted to show you this particular aspect, but I want to show you it actually working fully. So if I come over here, the first thing I'm going to do is run netcat. It's going to listen on TCP port 5555. This would basically simulate the attacker's computer waiting for that reverse shell from the victim to reach back out and hopefully get a shell, an interactive shell. So we have netcat listening on the port, waiting for a connection from the victim computer. So now I come over here. Here's my program that I'm going to self-ROP. This is the same one that we did GDB on, except this time I'm just going to let the program run by itself. So obviously I had some just benign print statements in there talking about applications and calculating storage and getting ready to install, blah, blah, blah. But here's just sitting here, right? It's just sitting. If I come over to my netcat now, and if I type pwd, right, that's the present working directory, I get an answer back. So right off the bat, I can see that I have a legitimate TCP reverse shell from the victim computer and the victim process reaching back out to me using my, the victim ran my program, self-ROPed itself, overflowed its own buffer, ran a ROP chain, did a TCP reverse shell and reached out. So I can run, any commands that I want, and all that kind of stuff. So this is just showing you how this works and what goes on with this. There's a lot of manual effort to kind of build this at first, but you can script these things up and make this a little bit more automated and a little bit easier to work with. Okay, we're back from the demo. So, what is the big deal? That seemed like a lot of work, a lot of complicated things. Is it really worth it? Isn't there an easier way? And some of you are saying, hey, that's really cool, that's really great, but couldn't you have just changed the bytes of that Metasploit code, and would that have gotten past the scanners? And to some extent, you are absolutely correct. I did that exact same thing. I took the code from the Metasploit binary and I altered it to add in some NOP opcodes. Those are basically do nothing operations in between all the real opcodes. And I took that binary and it was still functional. It still did a reverse shell, but I threw it up the virus total. And what did it show? It showed 0 detections. So yes, in terms of static signatures, doing an alteration of the bytes of a shellcode would work just as well as ROP and would be much easier to implement. So why do ROP? Isn't there an easier way than doing all this stuff? Well, here's my theory, and here's my thought on this. Attacks are multifaceted. They never are just about a single technique. If you try to simply modify the shellcode, on the face of it, just insert some different bytes, eventually the tools are going to get smart and they're going to see that. And instead of looking for a signature of bytes, they're going to look at a series of bytes and kind of distill them down to like, what would this do? If I was executing it, what would they do? And they would see in summation that those opcodes would do the same thing functionally as the shellcode, even though they have extra bytes in the middle of them. So defensive tools are improving all the time. Self-ROP really gives inherent and powerful obfuscation for static analysis that the simple shellcode polymorphism does not provide. You have a much deeper level way of hiding the true intent of a program from a static analysis standpoint. We're not talking about dynamic, but from a static analysis, it really does hide it much better than just trying to do alteration of bytes in shellcode. And I hope you saw that in the demo, especially when we looked at the source code of the program, that you can dress it up to make it look extremely benign. And unless you do a lot of low-level reverse engineering to understand the program or a bunch of dynamic analysis, you're not going to really see that it's going to overflow itself and run a hidden ROP gadget chain. What about the future of ROP? Is this going to be around forever? Is it unstoppable? Well, there are new features out there that look to mitigate these types of attacks. There's stack canaries that will look for overflowing of stacks. Remember, during the demo, I had to compile the program in a certain way to disable the stack smashing detection. There's also control flow guard and control flow integrity. Those are specific CPU options that will try to track a program as it was written. And if they detect the program executing in a way different than it was written, they'll stop it. So some of those mitigations that are coming down the pike are very powerful to try and stop ROP, stop JOP, and so forth. What's going to come after that in terms of defenses or new attacks? Who knows? Things are changing all the time. So certainly we're not just going to sit here and say ROP is the end-all be-all of it. It's something that's useful now. So from a red perspective, it is here to stay. But it shouldn't be used by itself. It should be used in conjunction with other things to round out attack technique and to try and be as quiet and comprehensively evasive as possible. From the blue side, I think what it shows is that signature analysis will not be enough. There still very much is a focus on signatures, and we need to get away from that. Detonation chambers, which are basically either on-premises or cloud-based VMs that try to quickly spool up and run a program and see what it does and gather information and telemetry on it. If those can get really fast and agile, that can be really useful against these types of attacks. Symbolic execution is a very, very powerful mathematical technique that basically allows a program to do what we tend to do as humans in our heads. You look at some source code and you kind of keep track in your head and say, oh, I think it does that, then it does this, and it does that. Oh, I know what this program does, right? If a detection tool could do symbolic execution, then that's a very powerful way of understanding the actual true intent of a program without actually truly executing it. However, symbolic execution is very, right now at least, performance hungry, and that could certainly be a trade-off that needs to be considered. It'd be interesting to see symbolic execution at the endpoint as opposed to in the cloud. And that could be very powerful and a lot faster of a capability to hopefully detect these things. I think, in summary, from a blue standpoint, what we see is that real-time behavior analysis is really the future. Again, we can't simply statically look and say, these groups of bytes, is it bad or is it not? We need to really be looking deeper and analyzing a program and saying, what will this program do? What will its behaviors be? And are those behaviors good or bad? The bottom line, either red or blue, right, kind of looking at purple in the middle, the bottom line is that it will always be an ever-evolving game of cat and mouse. The tools will get better both on the attacker side and the defender side, but I think the defenders have to stay abreast and aware of the latest of what the attackers are doing, what they're looking at, so that they can keep up with this. So how do we learn more about this? If you're really interested, if you want to play around with this, first of all, it might seem a bit like a cop-out, but it's not, because I looked at the Wikipedia page for the basics of ROP, and it is very, very comprehensive and put together. So if you want to start with a good place to jump off to various pages and blog articles and so forth, start with the Wikipedia page for return-oriented programming. There are also a lot of good tutorials on YouTube for how to do it, but I would start with the wiki page. The tools that I used, the primary one I showed you during the demo was gadget, and that one is up on GitHub, free to use. It's great. Another one that I have used that's got some powerful gadget searching tools is ROPYr. That's another one that's up on GitHub for free to use. So check those out, and if you have any questions, let me know. Okay, I want to thank you for giving me your time after lunch and being able to talk about some interesting research and techniques that I've been working on and how to ROP yourself. If you have any questions, my email's on this slide, or you can always ask any of the conference staff and they'll know how to contact me. And I would love to hear from you. I'd love to answer any questions that you have, help you in your journey to learn more about this. And again, thank you very much.